It's a whole 1 meter rule. So this is the diagram. Now, place the meter rule on the knife edge with its scale facing upward. Adjust the position of the knife edge until the meter rule balances horizontally. Then record the point of balance, capital G, and the point for a uniform meter rule, the point of balance will certainly be at the middle. So use one of the loops of string to attach the 20-gram mass hanger. So there's a hanger. The hanger has a mass of 20 grams. Then securely at G. Do not change the position of the hanger throughout the experiment. So this hanger position at G, we are told to maintain the position throughout. So theoretically, we expect that G would be at the 50 centimeter mark, which is the middle or the midpoint of the meter rule. Attach the mass X securely at a distance AP. The end is A, this end is A, and then P. AP, which is 2 centimeter on the meter rule. The position of X should also be kept constant throughout the experiment. So it means this position of X, which is 2 centimeter on the meter rule, must also be kept throughout the experiment. Then add a 20-gram slotted mass to the hanger and record the total mass of the hanger and the added mass to be 40. Okay, adjust the position of the knife edge. So this is the slotted, the hanger has a mass of 20 and you are adding on, starting with 20 grams. Then you adjust the meter rule till you have a balance point. Okay, adjust the position of the knife edge until the meter rule balances horizontally as shown. Read and record the balance JQ. I think the position of the pivot when balanced is denoted as scale. So you read and record the distance JQ after balancing the whole arrangement. All right, then evaluate D inverse and then repeat the experiment for 4 other total mass. M is equal to that. Okay, and so 120. So in each case, read and record D and evaluate the inverse. So tabulate your results. So this is the question, the practical or T question on moment. Okay, let's use our theory. Then the graph, please, when you come in, mute yourself for us. Okay. Plot a graph with M on the vertical and D inverse on the horizontal axis. Starting both axes at the origin 0. Then determine the slope of the graph and intercept on the vertical axis. Then if in the experiment M is equal to 70. Okay, so this is the issue. So let's use our theory to see how the graph. Please mute yourself when you come in, else I mute the whole house. I think I rather would have to mute all. So when there is a need for you to talk, then you come in. So let's use our principle of moment to determine how the graph will look like, and then the slope, deduce the slope and all that. So using principle of moment, this will give us anti-clockwise moment. This will also give us clockwise moment. So clockwise, anti-clockwise. Therefore, the first principle of moment, or the second one, total clockwise movement must be equal to the total anti-clockwise movement. So x times, what do you think will be the perpendicular distance of x from the pivot? What will be this distance? Please, a volunteer to help us out. What will be the perpendicular distance of x from the pivot? Yes. A volunteer. Let's not waste time. What will be the perpendicular distance of the Herbert?
Sir, please, 30 meters.
Herbert, what's your reason?
Sir, 30 meters.
But I mean, what is your reason for arriving at 30?
Sir, because they said that the length of the meter rule is 1 meter. That's 100 centimeters.
Exactly.
And from the pivot, it means that it is dividing. It means at this side 50, the other side 50.
Herbert, the
So
point G divides the meter rule because that's the center of gravity.
okay.
The point G divides the meter rule. Okay, so yes, if we are considering the point G, then 50, 50. But we are looking at this perpendicular distance of x, meaning we are looking at PQ, the distance PQ. Are you okay?
Yes, sir.
So look through it again. Yes, Amma.
Sir, please, I think PQ is 48 minus D.
I think I agree with Amma because you see this pole distance is 50. So if this is 2, then PG is 48. So if PG equals 48 and PG is equal to PQ plus QG or JQ. At the moment, PQ is what I'm looking for. Therefore, PQ would be equal to the remaining, which is 48 minus JQ, which has been given as D. So 48 minus D would give me PQ. Herbert and the rest of you, are you okay?
Yes, sir.
All right, thank you. So that is how to analyze it. Therefore, the turning effect or moment produced by X will be equal to the mass X times 48 minus D, which is equal to, what do you think will be the turning effect produced by the slotted mass M? Yes, Herbert, what will be the turning effect produced by it? By the slotted mass M? If there is a need for us to answer, let's quickly do so and move on. Else I come in. So this will also be M times D. Okay, the mass times the perpendicular distance. Now we are asked to plot a graph of M on the vertical and D inverse on the horizontal. So let's expand this. This is 48x minus xd is equal to md. Our vertical is m. So this is similar to y is equal to mx plus c. The vertical axis must be made as the subject. So from our equation, there is a need of us to make m the subject. Okay, but before then, we must divide through by d because the x-axis is D inverse. So when we divide through by D, is equal to MD on D. We'll arrive at M is equal to 48x D inverse minus x. That becomes the equation of the straight line which eventually will be plotting. Okay. So from this, when we compare these two, y is equal to mx plus c, we realize that the slope, our slope would be equal to 48x. The slope of the graph must be 48x. The intercept on the vertical axis, C, is equal to negative x. Or what we have to do, because the equation is negative, this is negative, the intercept is negative, the equation must be written as minus C. Okay, usually when this is plus, this will be plus. When this is minus, that minus. So that C, okay, will be equal to x, because at the end of it, we are interested in the magnitude of the value x. This being negative, what I will interpret later on. So how would the graph look like? This is how our graph will look like. We are plotting a graph of M on the vertical and then D inverse M on the vertical axis, then D inverse on the horizontal axis. Now, because our slope, which is this, is positive, it means the graph will be a positive graph. The intercept on the vertical axis is negative, so it means the graph will cut the vertical axis at the negative side. This is 0. Don't forget, we are starting both axes from 0. Okay, so this is the point where the graph cuts the vertical axis. So just when you are given such a question, this is how your graph must look like. Okay, in determining the slope, don't forget, once it's a linear graph, any 2 points chosen on the graph can enable you find the slope. Any 2 points, whether up here, down here, or over here, or here. Any 2 points chosen. A large triangle, vertical, change in horizontal, must give you the slope. So, the slope. So let's look at the question and then answer the sub questions. So determine the slope of the graph and intercept on the vertical axis. So from my equation of the graph, the slope is equal to 48x. And last time I told you that in exams, this mass is actually known by us. It is covered with this paper tape, masking tape. So it is actually known to us. And this year, the mass that was used as S, this was 50 grams. So it means theoretically, your answer must be 48 times 50. And I think this is 2,400. Okay. Now, let's look at something. If X is 50, this mass is 50. And X, this X is the mass. And then 48. Don't forget 48 is PQ. Oh, sorry. 48 is this distance, PD. Okay. So it means that our slope represents the turning effect produced if the pivot had been at the center of gravity, G. It is the moment produced if the pivot had been at the center of gravity, G. Okay. And so the unit of this will still be in gram centimeter. Because if you find changing the vertical over the change in the horizontal, you realize that your slope will be equal to the unit, gram over centimeter per centimeter. This is, yes. So when it comes up, you have gram centimeter. So it means that the slope represents the turning effect if the pivot had been at the center of gravity. Then we are to determine the value of the intercept. The intercept C is equal to X. And what is X? X is the unknown mass. So theoretically, because the mass given is 50, we expect you to have a value of 50, around 50 grams. So the intercept on the vertical axis also represents the unknown mass X. Please, is that clear? Class, is that okay? Then,
Yes,
then calculate that using the equation. As for this, Z is equal to 100 plus your slope over 50. Okay, once you get your slope correct, okay, when you put it in, you can easily calculate for Z. And Z also represents the mass of the meter rule. Let's look at something. This is 100. Theoretically, our slope is 2,400 divided by 50. So technically, we have 2,500 divided by 50, which is 50. So the meter rule, the 50, that being equal to 50, also represent at least the mass of the meter rule. Okay, but one thing you must take note of is that assuming we were given the mass of the meter rule, it would have been added to M. But in this case, we were not given, neither were we told to calculate for the mass of the meter rule. So if we had been given, you were asked to measure and record, then the mass of the meter rule would also add to this. So in subsequent situation, if there is something like that, please, that is how, because the mass, uniform mass of the meter would act as G. And so if you had been given, it would have added to this to give the turning point. Okay. The remaining questions isn't any troublesome one. The next question is, if in the experiment M is 70 grams, use the graph to determine the balance length D. So if in the experiment M value is given as 70 grams, you have to use the graph to determine it. So assuming this is 70, you trace 70 to the graph, then you read the corresponding D inverse value. Okay, so 70 would give you a corresponding D inverse because D inverse is 1 on D. Assuming you had maybe 30 or 20 or whatever, you can easily calculate D out of it. So this shouldn't be a question that must trouble you when you face something like that. And then state the conditions necessary for a body to be in equilibrium under parallel forces. This one, you have answered it before. The principles of movement. Then define moment of a force. Okay. These are sub questions. So this is the problem as given to you last week. Okay. So please, with this understanding, whenever you are given a question on movement, use the principle of movement and then create an equation out of it. Okay. Then you can use it to deduce how your slope, your intercept, and all that must be. It isn't difficult at all. Please, any question? Any question? Charlotte, any question?
Okay.
Okay. Herbert. Okay, Galazi, please go ahead and answer.
Sorry,
Mhm.
sorry, I didn't have any. Sir, please, is it only when the mass is at the center of gravity that you need to add the mass of the uniform meter rule to the mass of the
Yes, you
substance?
see, for when the beam, the bar is uniform, its mass, total mass acts at the center. Okay, meaning if it isn't a uniform meter rule, it will not be at G in the first place. So if it's a uniform meter rule and you are given a mass is placed there, then the mass of the uniform rule itself would add to it. In this question, it was not talked about. That is why we didn't factor into our calculation. Are you okay?
Yes, sir. Thank
Okay,
you.
Amma.
Please, I wanted to ask that if the slope is not passing through the origin, like this graph, would they still ask for y-intercept and s-intercept?
Oh, in some situations, this question would have also asked for intercepts on the horizontal axis. Okay, once it doesn't pass through the origin, meaning the graph cuts the vertical axis and then the horizontal. So they could have equally asked for intercepts on the horizontal axis. Are you okay?
Yes, please.
All right. Then let's go back to the challenge, which challenged a lot of you. Some of you submitted it. Submit it, do it, and then get 2 gig data. But anyway, somebody got it. But the person is not here. Do it and then win 2 gig data. And Charlotte, I didn't hear from you. Amma, I didn't hear from you. Herbert was heard from. I think Lizzie also submitted hers. Equia Adoma, I saw it this morning. Yaba, nothing was heard from you and the rest of you. So the challenge question was that The distance between an object and its upright image is 20 centimeters. So this 20 centimeter value, some of you were taking it as image distance, object distance. He said the distance between an object, so distance between an object and its upright. Let me change the marker. The marker itself is not upright. And its upright image. Okay. So simply object and image, we are told is 20 centimeters. If the magnitude of linear magnification is 0.5, m we are told is equal to 0.5. But this m, oh shit, what is happening? So magnification m, we are told is 0.5. Determine the focal length of the lens. Now, my first question to the class is that, what kind of lens is this? What kind of lens is this? Yes, anybody?
Sir,
Yes.
sir, please, I think it's a divergent lens.
Divergent or oh, yes, divergent or what kind of lens?
Sir, please, I don't really.
Divergent, hey, somebody else, Eura, divergent or
Or a concave lens.
okay, so divergent or concave. No, Herbert, you are right. But can you tell me why you think it is? You think it's divergent lens or concave lens? What informed your thoughts?
Sir, it's when I solved this,
Mm,
I had
anyway,
a negative.
it's an open question to the house. Can somebody tell us why you think this must be divergent or concave lens and not convex or converging? Can somebody tell us? Adjoa,
The image is upright. The vector.
the image is upright and
Virtual.
once the image is upright, it means it is virtual. Equia is also saying that it's because the image is upright and diminished. Yes, it is. The image is upright. Once the image is upright, it means it is virtual. Now we are also told the image is diminished. You see, the reason is that, yes, convex lens also forms a virtual image. But the virtual image formed by a convex lens is always magnified. There is only one position where a virtual image is formed in convex lenses. That is when object is placed between the optical center C and then the focal point. And this position of object will produce a virtual image that is magnified. Concave mirror lens, on the other hand, would always produce a virtual image that is diminished. And so once the image is erect, which means it's virtual and diminished, then the lens must be a convex lens. Okay, now if it's a convex lens, then let's use ray diagram. You know, for convex lens, no matter where you place the object, the nature of image form is always the same. So if this is F, this is the optical center C. We have another F here. This is 2F, center of curvature. We have another 2F. And I'm doing this because this is biconcave. Bi. So wherever you place the object, assuming the object is here, let's use ray diagrams. A ray of light parallel to the principal axis after refraction, this will diverge, and the diverted ray appears to be diverted from F. Then a ray of light passing through the optical center goes undeviated. Do not also overlook the fact that for concave lens, the image is always closer to the lens. Okay, so the image is here. So this is the object. From optical center to the image gives us V, image distance. From the optical center to the object gives us U. And this is the distance given to us, that the distance between an object and its upright image is 20. So this is the distance that was given. The image object. So this is the 20. So by magnitude, we could deduce that then object distance U is equal to 20 plus V by magnitude. U is equal to the image distance plus 20. Class, are you okay? Hello, are we fine with the illustration? Two. The second point is that we are told magnitude of linear magnification is equal to 0.5. Linear magnification, this is equal to V over U. So it means that V is equal to 0.5 U. Image distance is equal to 0.5 U. Now using the lens formula, 1 on F is equal to 1 on U plus 1 on V. Image is virtual, and using RP. In lenses, we often use RP. Even though we can use NC as well. Using RP, the focal length of concave lens is negative because it's virtual. It's virtual. So minus 1 on F is equal to 1 on U, which we don't know, The image is virtual as well. So minus 1 on 0.5 U. Here, if we factorize out 1 on U, we have 1 minus 1 over 0.5. Yeah, are you here?
Yes, please.
What we have? What is 1 minus half? 1 minus 1 over 0.5. 1 over 0.5 itself is 2. So we have 1 minus 2. This is giving us minus 1 on F is equal to minus 1 on U. Therefore, U is equal to F. U is equal to F. Okay. Therefore, U is equal to F. Now, if U is equal to F and we have V to be this, don't forget we have U is equal to 20 plus V. And here, I'm not negating V because I'm considering the magnitude of the object distance, image distance, and then that separation between them. Okay, so if I substitute whatever I have here for V, I have U is equal to 20 plus 0.5 U. So help me find U. Help me calculate the value of U. When you get it right, quickly draw our attention. What have we had as the value of U?
40 centimeters.
So U is equal to 40. So once U is 40 and U is also equal to F, then it means F is also equal to 40 centimeters. Yes, some of you got it right by getting F is equal to negative 40. Okay. Yes. The negative is just to tell you that the focal length F is virtual. But in terms of magnitude, it means the lens has a magnitude of 40 centimeters. That is all. Please, is there any question? Charlotte?
Stay there.
Any question?
No, please.
Amma,
Yes, sir.
do you have any question?
No, please.
Herbert?
Yes.
Any question?
No, sir.
Aura? Okay, so this was a challenge. It isn't difficult, but you need to, think a bit deeper into it. Okay. Let me quickly drop attendance. Take attendance and drop it in the group. Okay. So give me a minute or two to do that.
Yes, sir.
What account for a body's increase in temperature and then decrease in temperature? Please, you can share with us if you have read around something like that. Okay. I just want your individual views, then we put that together. Okay, Gerald, Doku, go ahead.
The internal energy of the body or the heat energy which rises and decreases. So let me say the internal energy.
So when the body's temperature is increasing, You said the internal energy, that's what?
When the internal energy
Mhm.
increases, that's where there's increase in heat energy. But when it decreases, then the heat energy also decreases.
So what Jeriel is telling us is that the heat energy possessed by a body has something to do with the internal energy of the body, which is true. Now, when a body's, you see, the total energy, which is the internal energy, which accounts for a body's energy, okay, it's made up of, has to do with the kinetic energy of the molecules of the body plus the potential energy of the molecules of that same body. Okay, so internal energy has to do with total kinetic energy plus potential energy of the molecules of the body. And here we are stressing on of the molecules of the body because we are not interested in whether the body is running. You see, when the body as a whole is running, it possesses more kinetic energy. But internal energy excludes the external kinetic energy of the body. Our interest is on the internal kinetic and potential energy of the molecules of the body, excluding the external Ke and Pe. Okay. Now, when the body's kinetic energy increases, average kinetic energy is directly proportional to the absolute temperature of the body. So here, all that we are saying is that when the average kinetic energy of the molecules of a body increases, the body's temperature also increases. Okay, that is why when you put your palm together and you rub against each other, okay, here friction results in increased energy of the molecule. So the moment kinetic energy of the molecules increases, the body's temperature also increases. So temperature relates to a change in the kinetic energy of the molecules of the body. When the kinetic energy of the molecules of the body increases, the temperature of the body would also increase. And don't forget, a change in the kinetic energy results in a change in the internal energy. That is how come the body gains much energy and could transmit from one body to another. So temperature, which is a measure of how hot or cold a body is, has to do with the kinetic energy of the molecules of the body. When the average kinetic energy of the molecules increases, the body's temperature also increases. When the average kinetic energy of the molecules decreases, the body's temperature also decreases. Now, the potential energy possessed by the body defines the state, whether it is in the solid state or it is in the liquid state or gaseous state. So when the potential energy of a body increases, what is happening? What happens is that the body begins to change state from one form to another. So the two things which contribute to the internal energy is that when the kinetic energy changes, it reflects in the temperature of the body. And when the potential energy of a body changes, it also reflects in the state or phase of the body. Okay, so let me put that down. So change in the average kinetic energy of molecules results in a change in temperature of the body. Change in the average kinetic energy of molecules results in a change in the temperature of the body. Then a change in the potential energy of the molecules or particles. Molecules of a body also results in a change of state or phase of a body. However, a change of state occurs at a constant temperature. Okay, so that is it. When a change of state begins, it occurs at a constant temperature. And this explains the reason why, you see, whenever solid is changing to liquid, the change begins at the melting point of the substance. Whenever we reach a temperature, we are calling at the melting point. So melting point is defined as the temperature where a substance changes from the solid state to the liquid state. Freezing point is a particular temperature where a substance changes state from the liquid state to the solid state. Okay, so every change of state occurs at a particular temperature, and this temperature is what we technically call as melting point, boiling point, blah blah blah. Okay, and so on and so forth. And so every change of state occurs at a constant temperature, meaning practically, whenever you put water on fire, and the water gets heated and gets to a temperature of 100 degrees Celsius. And that is the point or the temperature where the water begins to change state from the liquid to the gaseous state. When this temperature is reached, if you have a thermometer dipped in the water, as you begin to heat the water, it will show in the change in temperature. You realize that the water's temperature will be increasing because of the absorption of heat energy. It would increase. When it gets to a temperature of 100 degrees Celsius, you wouldn't see any change in the temperature again. The water will continue to boil on and on and on and on. There wouldn't be a change in the temperature 100 degrees Celsius. Okay? Until every water has turned to vapor. But at that point, you have no water even in the vessel for you to even observe. So every change of state occurs at a constant temperature, which is either the boiling point, the melting point, the freezing point of the material. Please, any question?
Please.
All right. So when we talk about internal energy of a body, we are referring to the total kinetic plus the total potential energy of the body. And this total kinetic and potential energy relates to the heat energy possessed by the body. So when a body has a larger internal energy, it equally has a larger energy to share with another body. Okay, so temperature relates to kinetic energy. Then the heat energy possessed by a body also relates to the internal energy possessed by a body. All right. A question to the house before we look at thermal expansion for solids. Why is it that burns sustained from vapor is so severe compared to burns sustained from boiling water?
Please come again.
I'll come again. Why is it that burns or injury sustained from vapor is so severe than burns sustained from boiled water? And we've all been to the kitchen before. We've seen this, we might have felt this before. Even the guys would attest to it, that when you sustain burns or injury from vapor, it's too severe compared to burns sustained from boiled water. Why?
Really?
Go to the kitchen. go to the kitchen and see. Okay, Gerald.
The degree Celsius, or let me say the heat energy, or the point where the heat is in the vapor is very higher as compared with the heat in the boiling water, because the heat in the vapor is like it has passed 100 degrees Celsius, but the boiling water has now reached 100 degrees Celsius. And so we see the difference in the heat energy when it burns your hands using the
Okay,
vapor.
I think that's excellent from Gerald. Please, another view. If you have any other view in a different way to share with us. Okay, Natalie.
Okay, so you see the vapor is gas, right? And the molecules in the gas are in constant random motion. And if they are in random motion, the kinetic energy of the molecules inside the gas is very high. So high kinetic energy also accounts for high temperature. That's why it gets severe burns because of the vapor as compared to the the boiling water.
Okay. This is also not bad.
Okay, sir.
More view. The last one.
Okay, sir, please. The reason is that the steam carries more heat energy than the boiling water. And the steam, and when the steam rises, it comes into contact with the skin, releasing heat from the vapor. And when the additional heat energy is released, it causes severe burns than the boiling water.
All right. Thank you for the contributions. I mean, all of you. But the key note was given by, okay, even though you were all giving me points, that is, I mean, so good. But the maximum information I needed was given by Jerry. You see, the note I just cleared indicates that every change of state occurs at a constant temperature. So when water is changing from liquid to gaseous, it must occur at boiling point, which is 100 degrees Celsius. So what happens is that if you put water on fire and you supply it with heat, okay, the water absorbs heat energy from the source. Then as the heat energy is absorbed, it increases the kinetic energy of the molecules and automatically reflects in the temperature of the water. So it will be increasing so long as it continues to absorb water from the source of fire. Now this will go on and on and on. Okay, heat energy supply, which reflects in the temperature. And the heat energy that shows up or reflects in a change in temperature of a body is termed as sensible heat. Sensible heat. So sensible heat is the heat energy, okay, that shows up in the change of temperature of a body. So the water will be absorbing this energy on and on. Its temperature will be increasing till the temperature gets to 100 degrees Celsius. At 100 degrees Celsius, we have reached the boiling point of water. And this is the temperature where water would change state from liquid to gaseous. Now, at that temperature, boiling point, there wouldn't be any change in the temperature again, even though the water absorbs heat from the source. So look at what is happening. The source is still providing water, okay, heat energy, okay, but the heat energy supplied at 100 degrees Celsius will not show in the temperature because it is beginning to change states. Okay, but the heat goes into the water body, and then this time what the heat energy supply, which does not show in the temperature, that is that it begins to break the intermolecular bonding between hydrogen, oxygen atoms. Okay, the extra heat energy supply does not work on the kinetic energy of the molecules, but this time the extra energy works on the intermolecular bonding, on the potential energy of the molecules. Okay, so once the bonding between the water molecules begin to break, it separates or releases them. Thereby, the water molecules begin to change state, because if they were not freely moving because the bonds are broken, they can move freely to change state. And that extra heat energy, okay, which goes to work on the potential energy of the molecules, is termed as latent heat. So we have sensible heat and latent heat. So sensible heat increases or changes source of heat, which reflects in the temperature of a body. Latent heat is hidden. Latent or hidden shows up in the change of state. Change of state of the body, or shows up in the increase in kinetic energy, shows up in the increase in potential energy of molecules. So when the water molecules are broken, the molecules are set free and they can change state. So what it means is that before water reaches what we can describe as vapor, it has both sensible heat and latent heat. Meanwhile, the boiled water only has sensible heat. So clearly, it means that water vapor contains more heat energy than boiled water. Water vapor has sensible heat, that heat energy which took it to 100 degrees Celsius, and also has latent heat, that heat energy which changes the intermolecular bonding, works on intermolecular bonding. So vapor has more energy than boiled water. Please, is that understood?
Yes.
So, Charlotte, this is what happens. If you have never seen it before, go to the kitchen after today's lesson.
Oh, Miss, yeah.
Oh, maybe you've not, you haven't noticed before. But burn sustained from vapor is so severe than burn sustained from boiled water because vapor has more heat energy, both latent and sensible heat, than boiled water, which only has sensible heat. All right. Please, if you have any question, don't hesitate to ask. And everybody, not some of you, I mean. Okay, so thermal expansion in solids. When we look at the three states, solids, liquids, and gases. Gases expand more than liquids and solids. Gases expand more than liquids and solids. Can somebody tell us why? Why is it that gases expand more than liquids and gases? Can somebody share with us the reason? Ama, Ajua, okay, Natalie.
Okay, so in gases, the molecules in gases are in random motion, and then they are not tightly packed as solid or liquid. That is why gases expand more than liquids and solids, right?
Okay, excellent. Excellent. More views. More views. Adoma, Lizzie, let me look at attendance. Let me look at attendance and come to you. Fosti, Festus, Herbert, Idrisu, Inshira, Jerry, Lizzie, Natalie, Oheneba, 1+, Othniel, Rich Love, Tuchi, Yaba, you are there. Adoma and Co. Okay, another hand is up. Go ahead. Jariel, go ahead.
Yes, please. So I was saying that gases move in a random and haphazard motion. So their molecules are not stable at one place. And when kept inside the container, they will spread around the container. Unlike solids that uh, they have their own shape and they can't be put in any type of container, as well as liquid that take the shape of the container.
Okay, so you are all right. I think another hand is also up. The hand is down. Okay, so the whole idea is that it is just because the intermolecular bonds in solids is more stronger than the intermolecular bonds in gases or the force. Okay, it's so more in solids and less in gases. So they can easily expand, okay, break and then expand. So solids, liquids, and gases expand more than liquids, and then I think the list is solids, followed by liquids and then gases, just simply due to the intermolecular forces. Yes, intermolecular forces. All right. So let's look at thermal expansion in solids. Thermal expansion in solids. Thermal expansion in solids is so conspicuous in solids. We see it all around us. The reason for which, whenever you are welding two solids, you need to compensate for expansion in solids. Else, there will be huge exertion of force on the two joint solids and can yield or result in a total collapse or breaking. Okay. New roofing sheets with time expand and then the initial very nice bright roofing sheet expands to be something. So thermal expansion is something which we really would have to consider. It's so conspicuous within the environs, and as disciples of physics, we need to be aware of thermal expansion. Now, if you pick a certain length of solid or rod of initial length L0, where L0 is the initial length of the rod. What are some of the factors we can possibly create a change in length of a rod of initial length L0? What factors do you think can cause a change in length of a rod of initial length L0? Or what can possibly be done so that its initial length can change, or factors which would affect a change in length? Yes, Adwa, can you tell us a factor on which the change in length can possibly rely on? Any idea? Okay, Amma.
Sir, please, I think temperature.
So the first obvious factor is that when you heat, when you increase temperature, it can affect the initial length of the rod. So change in length is directly proportional to temperature or change in temperature. So first, the change in length of this is directly proportional to change in temperature. Initial temperature, this, when you heat it to another temperature or a certain final temperature, it would affect its change in length. Another factor which can also change its bring about change in length has to do with the initial length itself. Initial length L0. This is because, in fact, if initially you have a very small, let me even use what I have. If I have a rod of this length and I heat it, subject it to heat energy, the difference I'll have has to do with what I initially have. What you have is what you get. If you have small, you get very small in addition. If you have a longer length initially, okay, this is because you have a longer change, because the change is linear expansion in solids. Solid expand linearly, okay, and then superficially, and then in volume, okay. So if you have a longer length, you have a longer length being added because solids expand linearly. Liquids and gases actually expand in volume, okay. They do not go through linear expansion or area expansion. Liquids and gases go through volume expansion, okay. So the change in length also has to do with the initial length because of linear expansion. Please, can we talk about any other factor which can affect the change in length of the original rod? Apart from temperature and then initial length, can we also think of any other factor, whether physical or hidden? Is there any? All right. So these are the physical factors which would affect the initial length. This means that let's relate them. The change in length, okay, of the solid or the rod is directly proportional to its initial length L0. This same change is directly proportional to the change in temperature, delta T. And in direct proportionality, when we connect it with an equal to establish an equation, we have a constant of proportionality, K. So K L0 delta T. This constant of proportionality K is what we term as lambda. It has a symbol which is the same as direct proportionality. So delta L is equal to lambda L0 delta T. Lambda is termed as the coefficient of linear expansivity or coefficient of linear expansion. Coefficient of linear expansion. Linear expansion or expansivity. Okay. Now, what is coefficient of linear expansivity? From the relation we have on the board, if you make alpha the subject, alpha is equal to delta L over L0 over delta T. Okay. And this is a measure of the change in length, a measure of the change in length per unit length, per unit degree or Kelvin rise in temperature. So linear expansivity alpha is a measure of the change in length per unit length per unit length per unit degree or per unit degree or Kelvin rise or Kelvin rise in temperature. So solids generally increase linearly or expand linearly. And alpha is the measure of how solids, okay, expand linearly in this form. Different solids have different linear expansivity, meaning that if you subject different solids to a change in temperature of 1 Kelvin or 1 degree Celsius, they can expand differently. As we move on, I'll give you values of the linear expansivity of different metals, okay, of different metals. Can somebody help me determine the SI unit of alpha, linear expansivity? Can somebody help me deduce the SI unit of linear expansivity? SI unit. Okay, Lizzie, go ahead.
Please, centimeters or meters.
Come again.
Centimeters or meters.
Look at it again. Alpha is equal to delta L over L naught delta T. Or let me make capital T. So if alpha is equal to delta L, change in length over the original length over change in temperature, what do you think will be the SI unit of linear expansivity? Abba?
Yeah, please. Per Kelvin.
Either, so this is equal to per Kelvin or per degree
Celsius.
per degree Celsius. So either per Kelvin or per degree Celsius. It is either per Kelvin or per degree Celsius because on the Celsius and Kelvin scale, a change in temperature is 1:1. So 1 degree Celsius change is equal to 1 Kelvin change. So that is why, so you see that unit is actually derived from delta L, maybe in meter, L not in meter. So they will cancel out. And what will be left is delta T. So either per Kelvin or per degree Celsius change in temperature. So this is what we mean by linear expansivity, the rate at which solids expand per degree or Kelvin rise in temperature. And different solids have different linear expansivity or coefficient of linear expansion. Let's look at area expansion.
Mr. Dear,
Hello.
please can you send your camera a little bit down? I want to write. Thank you. Please, I'm done.
So,
thank you so much.
All right. Solids also undergo two-dimensional expansion.
Please, you can send it back up. I'm done.
Okay. Area expansion. So, if you have an initial area, A naught, of length L naught, initial length, then width B naught. The initial area is actually A naught. And then of initial temperature T1. T1 equals initial temperature. Now, if you subject this area to heat energy, because solids expand linearly, its length, which is linearly, would expand. Its width, which is also linear, would also expand, thereby affecting the whole area. And so the change, when you subject it to change in temperature, the change in area is also determined by the original area, A0. The change in area is also, or would also be determined by the change in temperature, delta T. Delta A is therefore equal to a constant of proportionality times the initial area or original area A0 times delta T. And this constant of proportionality K is what we are calling as beta, coefficient of area expansion. So delta A is equal to beta times A0 times delta T. Beta is termed as the coefficient of area expansion, beta. So let's establish something. In linear expansion, I have an original length. After subjecting it to heat, I have an addition. Let's assume it is this. This addition is delta L. It implies that the final length L, let's represent L1. Let L1 be equal to final length. Okay, after heating. So it means that the final length L is equal to L0 plus the change in length. The final length L is equal to L0 plus the change in length. The change in length comes up after heating. And so L0, which is the final, is equal to the initial length plus change in length is equal to alpha delta L, alpha L0 delta T. The change in length is equal to this as we saw. Therefore, L, which is the final length, can be equal to L0 factorized out times 1 plus alpha delta T. This is a new expression for the final length. An expression for the final length. Don't forget, we can also determine the same thing because L is equal to L0 plus delta L. Use this to calculate for delta L, then come and add it to the initial length. And that will also give you the final length. Okay. So whenever you are to calculate for the final length, either you use this or you go this way, knowing that delta L is equal to alpha L0 delta T. You find this and add it to the original length. That is also another way to go. Now we can also do the same thing for Festus.
Please, with the area expansion, I don't really get how you develop the equation.
I'll come back to it. Don't worry.
Okay.
So area expansion. What we have is that we have an initial area of sheet. Okay, a two-dimensional something like this. Okay, like this book. This is my initial area. Then I subject this to temperature or heat. Okay, because solids go through linear expansion, its length would increase, its breadth would also increase. So what I've indicated is that after subjecting this to an initial a temperature, initial temperature is T1. Then we heat it to a final temperature T2. So T2 is equal to the final temperature. Heating this, okay, would change the area. Heating the area, the initial area, will certainly add something to it because the length goes through linear expansion. The weight also goes through linear expansion. So let's assume after heating this length increases to this point. So this is the change in length, delta L. The weight also increases to this. This is also the change in the weight, delta B. So we realize that the new area would be this. With that increase, then the weight would also be this and would be different from the initial area. So this is A, the final area, with length L0 plus delta L, with weight B0 plus delta B. Okay, but this will happen upon subjecting this to heat energy. So this is final length L. This is final weight B. Please, Festus, are you okay?
Yes, sir.
All right. Now let's pick expression for each one of them and look at the expression or the relation for the final area and how area expansion depends on linear expansion. A0 A0 is equal to L0 times B0. And A is equal to make it proper, let me make it L1 and B1. A is equal to L1 times B1. So this is initial area. This is final area. So the final area A is also equal to A0 plus the change in area. What is the change in area? The change in area is equal to coefficient of area expansion B times original area A naught times the change in temperature. Okay, that we obtained earlier. That change in area is directly proportional to the original area and then the change in temperature. So when we equate and then bring in beta, we have beta A naught delta theta. So we are only adding this expression to what we have here. Meaning we can factorize out A naught. So we have 1 plus beta delta T. This is the expression for the final area, A. Okay, this is the expression for the final area, meaning it's the initial area times 1 plus whatever we have this in bracket. Now let's look at the relationship between linear expansion and area expansion. Okay, the relationship, we can actually prove that area expansion is equal to 2 times linear expansion. But let's go through the proving. There is the need for you to understand and apply this. So we have A1, the final area, equal to L1 times B1. What is L1? L1 is equal to original length plus change in length. So this is equal to L naught plus alpha L naught delta T for L1 times B1 is also B naught plus beta times B naught times alpha T. Let me write it here for you to follow the steps. So L naught plus alpha L naught delta T times B naught plus alpha B naught times delta T. Please, are you okay with the two expressions? If you don't understand an aspect, then I quickly come in. Are you okay with that?
Yes, please.
Okay.
Yes, please.
All right. In this term, we can pull out L naught. 1 plus alpha delta T times, we can also pull out B naught. B naught out 1 plus alpha delta T. Meaning we have L naught times B naught. Then 1 plus alpha delta T squared. This time this, so squared. Now when we expand this, if we expand what we have within the bracket, L naught and B naught is actually A naught. It's actually A naught, the original length. Expansion of this is equal to 1 plus 2 alpha delta T plus alpha squared delta T squared. That's the expansion of what we have within the bracket. Now, alpha squared is approximately equal to 0. This is because in fact the coefficient of linear expansion of solids or metal very, very small. very, very small. I have that of aluminium right here. And the linear expansion of aluminium is equal to 0.0015. I think 0.0015. Meaning, if you heat aluminium by 1 degree Celsius or 1 Kelvin, it will change by this amount, very, very small. So because the linear expansion or expansivity of metals is very, very small, when you square it, whenever you square the linear expansion of metals, it is almost zero. Look at squaring 0.0015. Square zero, what I have here, and check it for yourself. So if it's aluminium, then 0.00015 squared is almost, the value is almost zero. If the value is almost zero, then whenever we have a square, a cube, a fourth power of this, the value is approximately equal to zero. So this part is approximately zero because of that reason. Class, are you okay?
Yes, sir. Yes, sir.
So we have A is equal to A naught 1 plus 2 alpha delta T. Now, compare this to what we had here. Compare this to what we had here. A is equal to A naught 1 plus beta delta T. When you compare, you realize that, oh, then this part can be equated to this. So beta delta T is equal to 2 alpha delta T. So that beta is equal to T, the change in temperature will cancel out. Beta will be equal to 2 times alpha, implying that coefficient of area expansion is 2 times the coefficient of linear expansion, meaning for the same temperature, if you have a metal, it will expand twice. Okay, a metal of a metal sheet of a particular area, it will undergo 2 times expansion as compared to if it's just a linear, a straight metal. Because this is about area. Metals undergo change in its length, would undergo change in its length as well as change in its width. So for the same temperature, metal sheet of a particular area would expand twice. Just as the relationship between area expansion and linear expansion. Please, any question? Any question? Charlotte, Herbert, Perry.
Yeah.
Are you okay?
Please, there was a point. My connection was bad, so I joined and then you had written a whole lot. I have to watch the video again.
Okay. So the next thing we have to look at is volume expansion. So if we are looking at a metal with length, width, and then height, it will undergo 3 dimensional expansion. It will go through its length would expand, its weight as well as its height. So the next thing to look at is volume expansion in solids. Volume expansion in solids. We are going through today. Tomorrow we'll start solving problems with whatever we've done today. Then move on to expansion in liquid. Oh, we have 3 minutes to go. I doubt if we can finish that. So if you have any solid, Ishra, or Ishra?
Yes, Studio. It's on mute.
Okay. I'm trying to draw a cuboid. Even though I've forgotten my isometric drawing. Yes. My primary school drawing of a cuboid. So this is L naught, initial length, initial width, and H naught at an initial temperature T. So at an initial temperature T, this is the original length, width, and height. After subjecting it to an increased temperature T2, the volume would increase, and we realize that the final volume V naught or V would be equal to the original volume plus a change in volume. The change in volume V is directly proportional to the original volume and then the change in temperature. And so therefore delta V is equal to, the constant of proportionality here is gamma, coefficient of volume expansion, gamma V naught delta T. And so V would be equal to V naught plus the change, which is V naught delta T. Your assignment is that I want you to prove that alpha is equal to 3 times, gamma is equal to 3 times alpha. That is your assignment because it's time. It's 9:31. So prove this for me, okay, before we meet tomorrow to discuss the solve questions and move on with it. All right. So class, this is where we draw the curtains on today's meeting. Thanks for your time. Please work this out. Please, you can get a trick by going through what we did for area. So go through it and then help me derive this. Until tomorrow, may the good Lord be with you and bye-bye.
Bye.
Hmm.